Good afternoon, everyone. Welcome to the Fluids and MHD seminar. So today we've got Basile Gallet from CEA Saclay. So he did his PhD in ENS Paris with Stéphane Fauve and Francois Petrellis. And he then did postdoc positions in Scripps Institute of Oceanography and in Orsay. And he's been in Saclay since 2014. And he'll be talking today about radiatively driven convection.
Okay, thank you very much. Thanks for the invitation. So indeed, I'll be discussing some laboratory experiments of thermal convection and in a setup that departs from the standard Rayleigh-Benard convection setup, and I will define what that is, in the way the fluid is heated up and the convection is driven. And that's work we've done with two grad students, Simon Lepeau and Vincent Bouillot, one postdoc, Benjamin Miquel, and Sébastien Omedre, who's another researcher working at CEA Saclay. Okay, so you probably know what thermal convection is. It's one way to transport heat. If you have a container like that and a heat source below it, the fluid will become warmer near the bottom, so it's going to be lighter. There will be an unstable superposition of heavy fluid on top of light fluid, and the instability will spontaneously lead to motion that will be turbulent if the heating is strong enough. Okay, and this convection is the way that nature uses to move fluid around, and that happens in these different systems. One you probably know better than I do is stars, where depending on the mass of the stars, you can have convective and radiative zones, and depending on the mass, you can have a direct overlap of the internal heating due to thermonuclear reactions and the convective zone, and that's going to transport stuff outward. There is the atmosphere, in which you have a peculiar form of convection that is impacted by moisture, and that's going to lead to the formation of clouds. You've got convection in the interior of planets, metallic convection, but also a convection of electrically conducting fluid in the outer core of the Earth that leads to dynamo effect and the magnetic field of the Earth. And you have some kind of convective motion in the oceans, although most of the kinetic energy is supplied by the winds. In fact, it seems that the direction of the currents may be set by the temperature gradient at large scale at the surface. And you have some peculiar form of slantwise convection near Antarctica here that is also called baroclinic instability or baroclinic turbulence. Okay, and so typically the way this convection has been studied, at least in the physics community and in lab experiments, is in the framework of the Rayleigh-Benard setup, and that's the Rayleigh-Benard experiment. The Rayleigh-Benard framework, you have two plates, a hot bottom one and a cool top one, and you have a layer of fluid between these two plates. So again, the fluid will become lighter near the warm plate and cooler and heavier near the cold plate. So you have an unstable superposition of fluid. It's going to induce turbulence. And what this turbulence is going to do is that it's going to transport heat from the hot plate to the cool one. Okay, so you could think of the same situation where you have a motionless fluid or even a solid that has the same thermal conductivity as the fluid. In that case, you're just diffusing heat from the hot bottom plate to the cool top one. But now, because the fluid is moving, you have another way to transport the heat, which is convection, and each parcel can just carry some heat from the bottom plate to the top one. So there's going to be some enhancement of the heat transport associated with the emergence of thermal convection. Basically, then the key question is how much, what is the heat flux P between the two plates as a function of the temperature difference delta T between the two plates. Okay, in fluid dynamics, we're going to ask this question in dimensionless form so that we have relationships between dimensionless parameters that we can, apply to any fluid of interest. And so we're going to non-dimensionalize delta T in this form to form the Nusselt number. Sorry, I have to move that. Here's the Nusselt number in terms of the thermal expansion coefficient of the fluid, the acceleration of gravity, the height of the layer, the thermal diffusivity, and the kinematic viscosity of the fluid. So that's a dimensionless delta T, and then we're going to non-dimensionalize the flux in the form of this Nusselt number, which is the flux divided by the purely diffusive heat flux. This is the heat flux that you would have if you had no convection, if you replace this fluid by a solid that has the same thermal conductivity. Okay, so basically, this question P as a function of delta T becomes what is the behavior of the Nusselt number as a function of the Rayleigh number, the dimensionless delta t. You have one last parameter that characterizes a given fluid. It's the Prandtl number. It's the ratio of the kinematic viscosity divided by the thermal diffusivity. Okay, so you'll be looking for a scaling law that relates the Nusselt number to the Rayleigh and Prandtl number, which are the two control parameters of that system. And most likely, you'll be looking for a power law dependence of the Nusselt number on these two numbers, Rayleigh and Prandtl. The goal being that you hope to have a scaling law that can be used as a constitutive law of the fully turbulent fluid, so that you can extrapolate to the extreme parameter values of natural flows, which you typically encounter in astrophysical systems. So. Okay, so what are the predictions for these scaling laws? And basically, we won't worry very much about Prandtl in the two first parts of the talk, and we'll be focusing on this exponent gamma. So as I increase delta t, how large is going to be the emergent heat flux? And basically, there are two theories for the value of gamma. The first one is called the classical theory. It's due to Malthus, 1954, and it predicts that this exponent gamma should be 1/3. The idea is the following. Well, indeed, if you force the flow very strongly with a large temperature difference, the flow will be fully turbulent. That means that you're going to mix the temperature field by vigorous turbulence in the bulk, but you still have a no-slip boundary condition at the two plates, so you won't have much fluid motion in the boundary layers here near the plates. Which means that if you want to transfer heat from the hot plate to the cool one, well, first you need to diffuse that heat across the boundary layers, okay, before it's efficiently transported by the turbulent flow. And in fact, this diffusion across the boundary layers will be the limiting process of Rayleigh-Benard convection, according to Malthus. Okay, if you want a scaling law for the heat transport associated with this diffusive transport across the boundary layer, you need to know the scaling behavior for the height of the boundary layer. And here the standard argument is that this boundary layer is marginally stable, which means that the height delta is such that if you form the Rayleigh number based on delta, you should get a number that is very close to the critical Rayleigh number for the emergence of thermal convection. The idea being that, well, if this layer were much thicker than this marginal value, then you would just induce convection and erode the top of the boundary layer. On the other hand, if it's much thinner, then it can just diffusively increase in size until it saturates at this marginally critical value, the height delta. Well, if you ask for delta to have this marginal value, where the Rayleigh number is equal to the critical Rayleigh number, you get a value of delta that is independent of the height h of the layer. You conclude that the heat transport is governed by processes that are independent of the height of the layer. So the flux P itself should be related to delta T in a way that does not involve H. And if you go back to the dimensionless parameters, you've got H cubed here and H here. So you need the exponent gamma to be 1/3 in such a way that you have H on both sides of the equality here, so you can just cross it out. Okay, so that's a standard theory. It leads to gamma equals 1/3. So that's all fine, but there's another theory which is equally appealing. And it's based on the very simple idea that in most turbulent flows, large-scale quantities are independent of the tiny molecular diffusivities, kappa and nu in our case. And if you ask for the heat flux to be related to delta T in a way that does not involve kappa and nu, you conclude that the Nusselt number should scale as the square root of the Rayleigh number times the square root of the Prandtl number. Now, depending on your community, this scaling law is referred to as the mixing length scaling law, I guess, in the astrophysical community. And it's referred to as the ultimate scaling regime in the physics community. And I guess it's called ultimate because it was believed that for Rayleigh-Benard convection, if you could drive the system in an extremely turbulent regime, ultimately you should reach this scaling behavior. However, so far it seems that most, if not all, experimental data point to Nusselt increasing like Rayleigh to the 1/3, which means that at least in the values of Rayleigh we can reach in the lab, no matter how large Rayleigh is, you still have a dependence of the flux on the molecular diffusivities kappa and nu because of the boundary layers near the solid plates here. So that's all fine, but it also means that maybe this Rayleigh-Benard setup is not a very good model of several natural flows. Okay, now I can provide you with two examples at least. Two examples of flows where you would guess that the boundary layers of the Rayleigh-Benard setup are irrelevant. The first one, again, it's stellar convection, where for large masses and low mass stars, you have a direct overlap between the heat source and the turbulent bulk convective flows, so no boundary layers there. Another example that I'm drawing here is frozen lakes in the spring. So Great Lakes, in the spring, they have a shallow layer of ice at the surface, but the sunlight can penetrate through the ice and heat up the fluid in the vicinity of the layer of ice. Because this water is below 4 Celsius, warmer water is heavier, and in fact, this heating will induce some convection in the system. We're forming some heavy fluid that's going to fall deep inside the lake. Okay, so that's the way you can mix these Great Lakes in the spring, even though they're covered with a layer of ice. So in these two setups, once again, the heat is input directly into the bulk turbulent flow, thus bypassing the role of the boundary layers. And so we're inspired by this flow to ask this question, can radiative heating bypass the boundary layers and produce this ultimate or mixing length scaling regime in a lab experiment? Along the way of the development of this experiment, this paper by Adrian and co-workers came out, which convinced us, this is a numerical approach where they indeed bypassed the boundary layers by tailoring the internal heating so that you input the heat away from the boundary layers. So it's the same idea using a numerical approach. Okay, so here is the lab experiment we came up with. You can see the fluid is here. It's a mixture of water and dye. It's inside a tank that has a transparent bottom plate, and we're shining a powerful spotlight at the tank from below. So the light will penetrate inside the tank, and it will be absorbed by the dye. And depending on the concentration of the dye, we can tune the absorption length L over which the light will be absorbed and the heating will take place. Okay, so we have this radiative heating, and then we impose the heat flux P that's related to the spotlight, and then we measure the emergent temperature difference using 2 thermocouples, one at the bottom and one at mid-depth. Okay, this is what it looks like. You need quite a powerful spotlight. To give you an estimate, this is the power of the spotlight that's atop the Eiffel Tower. If you've been to Paris, quite a powerful one. And I guess that's it. And you need to filter the infrared radiation here to have only heating in the form of visible light, because the infrared would be absorbed directly in the vicinity of the plate, which is not desirable because that would be a heating that resembles the Rayleigh-Benard one, which is something we want to avoid. Okay, so once again, a key feature of this experiment is that we can tune the absorption length L. And we'll be focusing on 2 limiting situations. So the volumic heating term, it will be something like that, a Q of Z that you have on the right-hand side of the temperature equation. It's P over L, and it decreases exponentially with the height Z inside the tank over this absorption length L. You have P, the heat flux, divided by L, so that if you integrate this guy from Z equals 0 to infinity, you recover the total heat flux P that is input by the spotlight. Okay, so the first limiting case will be when this L is much less than the typical boundary layer of the temperature field in the system. Well, in that case, in black, you can see this source term Q of Z. The L is very small than delta, the boundary layer thickness, which means that you're inputting much of the heat directly inside the boundary layer, and that heat still has to be diffused across the boundary layer before it can be transported by the bulk turbulent flow. That's a situation that is very similar to a Rayleigh-Benard system, and so you expect an exponent gamma, which will be 1/3 similar to the Rayleigh-Benard setup. More interestingly, we'll be then considering the situation where the absorption length L is much greater than the boundary layer thickness delta. In which case, Q of Z has this shape in black. This is the boundary layer, and we're inputting much of the heat directly inside the bulk turbulent flow, away from the boundary layers. And so we expect, the relation between the heat flux and the emergent temperature difference to be governed by bulk turbulence. Okay, so that's all fine. But there's one trick. I haven't told you how I'm going to cool down the fluid. The reason is that we don't want to cool down the fluid with a solid plate, because in that case, we would have a boundary layer near the solid plate, and that would be similar to Rayleigh-Benard geometry. That boundary layer would throttle the heat flux. So instead of that, we decided to not cool down the fluid. So what happens in a convection experiment if you have insulated boundaries and you do not cool down the fluid? Well, you would write down the temperature equation in the Boussinesq framework. So you have the advection term, the diffusive term, and you have a source term here associated with the radiative heating, okay, decreasing exponentially with time. You can average this equation over space inside the tank, and you get this T bar, which is the spatially average temperature. The equation for T bar is very simple. It's dT bar dt equals a constant. Well, it's saying something very simple. If you're inputting heat at a constant rate inside an insulating tank, then the temperature will rise linearly in time. Okay? And from the slope of this mean temperature as a function of time, we can deduce exactly the power P that's input in the fluid. But then you can introduce a new variable, which is T minus T bar, and we will call that theta. If you write down the equation for theta, it's an advection diffusion equation that is now subject to a source term, the radiative heating, and a uniform effective cooling term that is going to remove exactly the same heat flux on average over the domain. Okay, so this variable theta is going to reach a statistically steady state. And if you measure any temperature difference T1 minus T2 inside the tank, you will get the same value than theta 1 minus theta 2 inside the tank. So any temperature gradient inside the tank is governed by this equation with radiative heating and effective uniform cooling of the system. Here's an experimental demonstration of what the raw signal looks like. So we are, once again, here is the geometry. We have these two thermocouples that are giving two temperature signals. The temperature at the bottom is larger than the temperature at the top. And a typical experiment starts with relatively cold water. Then we turn on the spotlight. We will rapidly reach a quasi-stationary regime where these two slopes, these two signals are parallel. Okay, so they have a constant slope, which is the drift rate of the mean temperature associated with the amount of heat that's input in the system. And then the delta T, the distance between the two curves, will be stationary, provided we're close enough to room temperature. So at first, it's slightly larger because you have some thermal leaks when the temperature is much less than room temperature. But when you're around room temperature, which was 24 Celsius for that example, the two lines appear to be parallel. Okay, if I want to convince you again that even though the temperatures are drifting, the system is in a quasi-steady state, quasi-stationary state, well, I can show you some snapshots of the temperature field at the surface of the experiment. We've done that by imaging the free surface with a thermal camera, and by doing so, you can see what the flow looks like at the surface by tracking the temperature structures. So here is what it looks like. This is the temperature field as a function of time. So you can see there is some warm fluid coming in, and then the cooler fluid falls down in here. In fact, it's compatible with a large-scale circulation, which is a single roll. You know, it's a turbulent flow, but the mean flow would be a roll that circulates inside the tank. And it all looks nice and quasi-stationary, even though if you look at the small numbers here, which are the color map, which is adapting as a function of time, we started here around 33.5, and it has increased. All these temperatures are increasing as a function of time because of the drift. Okay, and it's now close to 30, yes, 34.5 now. Okay, so the temperature is drifting at any single point inside the tank, and yet the system and the flow are in a statistically steady state. So from a typical run like that, I can measure P from the slope of the temperature signals, and I can measure delta T from the difference of the two signals in statistically steady state. So I can compute the Nusselt number and the Rayleigh number. And here is Nusselt as a function of Rayleigh for the two limiting situations. The first one, once again, is when this absorption length is very small, much less than the bandular thickness, in which case we expect to be in a Rayleigh-Benard-like case. And indeed, you can see the data points here in blue, and the parallel fit leads to an exponent, gamma equals 0.31, very close to the value 1/3 predicted for the classical regime of Rayleigh-Benard convection. Now, more interestingly, if you use a larger value of L, which is h divided by 20 here, you can see the data points in red here, and the parallel fit leads to an exponent, which is 0.54, very close to the value 1/2 associated with the mixing length or ultimate scaling regime. So I believe this is a very clear laboratory demonstration that we can achieve this scaling regime by bypassing the bandulars using this radiative heating in the system. Because this is a new setup, we wanted to confirm that numerically, so we used Daedalus to run a few numerical simulations. And you can see the numerical results here which lead to parallel behaviors with exponents that are very close to the values we obtained experimentally. The prefactor is slightly different. It could be due to the Prandtl number being not exactly 7 for water, or maybe because the DNS are done in a cubic geometry instead of the cylindrical geometry of the lab experiment. Okay, if you look at a typical snapshot at a very qualitative level, you're looking at temperature here, and the temperature field for Rayleigh-Benard convection, the large values are really confined to the bottom boundary where you have to diffuse across boundary layer, thus inducing large delta T's near the bottom. If you look at a snapshot in the ultimate regime, you get that the thickness of this large temperature region is typically the absorption length for the light, and then you have plumes that are wider and penetrate deeper inside the bulk of the flow. Okay, so that's the summary of the first part. We were inspired by these natural flows to try to develop a lab experiment where we could bypass the role of the boundary layers of a Rayleigh-Benard experiment to try to achieve the ultimate scaling regime or mixing length scaling regime in a lab experiment. Okay, so that's interesting, but it also asks new questions from the point of view of fluid dynamics. Specifically, we've seen that by changing the absorption length L, we can transition from the Rayleigh-Benard regime to the ultimate one. In other words, we have a new dimensionless parameter, which is this dimensionless absorption length L divided by H. So now the Nusselt number should be a function of the Rayleigh number, of the Prandtl number, but also of this new dimensionless parameter. And most likely, we would expect a parallel dependence in each regime as a function of this new parameter L over H. So we still have Rayleigh to the gamma, Prandtl to the chi, but now we have L over H to the beta. Okay, and we'll be focusing on determining the value of this exponent beta. So Vincent Bouillot went back to the lab and he performed a lot of experimental points. Like you can see, it's quite a lot of work. And that's, every color or symbol is for a given value of the dimensionless absorption length L over H. So for very low absorption length, you get these data points here with Nusselt evolving like Rayleigh to the 1/3, slightly less, so a value close to 0.31. And as you increase L, you bypass the boundary layers and you transition to this Rayleigh to the 1/2, okay? And we'd like to understand the dependence of the Nusselt number on this L over H. So we came up with a very simple role model to try to explain the dependence of the Nusselt number of this dimensionless absorption length. So the idea is the following. We've seen that the large-scale flow seems to be compatible with a dominant large-scale circulation that circles around the tank in a turbulent fashion. So let's follow the trajectory of a given fluid parcel as it goes around the tank. So it will be at the bulk temperature here, the temperature of the bulk, until it enters the heating region here of height L. Then it will travel from this corner to this corner inside the heating region. And that's where it's going to increase temperature from the bulk temperature to the bulk temperature plus delta T, the typical temperature difference in this experiment. And then it's going to rise and mix with the bulk in a turbulent fashion and relax to the temperature of the bulk. Okay, so if you follow this fluid parcel, well, you write the Lagrangian derivative of the temperature. So the temperature, as we follow this motion here, will be governed by the source term in the temperature equation, okay, which is the radiative source evaluated in the heating region here. It travels over time h divided by u for a square cell, where u is the typical velocity in these experiments. This is a free fall velocity, which leads to, delta T will be the heat source multiplied by the time to travel from here to here. And this travel time is h divided by u. You substitute this free fall velocity, capital U, and you get that the Nusselt number should be L over H times square root of Rayleigh-Prandtl. Okay, so with this very simple model, we get the answer that the Nusselt number should depend linearly in the absorption length L. So we can try that, compare that to the experimental data, and to it, we followed the following idea. We said, well, for small Rayleigh number, what should happen? And for a given L and small Rayleigh number, the boundary layer thickness will be much larger than this L. So we should be in a Rayleigh-Benard regime where we're inputting the heat directly inside the boundary layer. But as the Rayleigh number becomes very large, the boundary layer becomes thinner and thinner. And at some point, this boundary layer will be much less than the absorption length L. in which case we're bypassing the bandulars and we should transition to the scaling regime. And the transition point between the two is when the Nusselt number is equal to the two scaling laws, where these two scaling laws are going to intersect. So this transition point is where the Nusselt transition equals both Rayleigh transition to the 1/3 and this mixing length scaling behavior. If you do that, you can get the coordinates of the transition point as a function of L over H. And so in the next slide, I will be plotting the Nusselt number divided by the transition Nusselt number as a function of the Rayleigh number divided by the transition Rayleigh number. Okay, and here's what you get. You can see this is all the data points with the different values of L over H that I've shown you before. And you can see that with these reduced Nusselt number as a function of the reduced Rayleigh number, all the data points collapse into a single master curve. So this is good news. It's an indication that indeed we've captured the right parameters for the problem. We have the right reduced parameters, so we have the right physics to describe the system. And this master curve, it follows a power law 1/3 in this region here for a low Rayleigh number. This is the Rayleigh-Benard regime, and it transitions to an exponent 1/2, which is the ultimate scaling regime when the Rayleigh number is large enough. Okay, so that confirms the prediction that the Nusselt number is a constant times L over H to the 1, Rayleigh to the 1/2, and we just have to determine the exponent in chi now. Okay, so if we want to have a fully closed scaling theory for the Nusselt number that predicts its dependence on all three control parameters, we need to understand the dependence on the Prandtl number. Okay, and now it's a bit tricky. According to the role model that I've shown you previously, we should get the standard mixing length regime. The Nusselt number would be L over H times square root of Rayleigh times Prandtl. However, this is still a real experimental tank, so we have a no-slip boundary condition at the bottom, and so there will be a boundary layer for the temperature field near the bottom. There will be a boundary layer, and so there will be a boundary layer correction to the temperature field associated with this boundary layer. Because again, we will be inputting some heat inside that boundary layer, and this temperature has to be diffused away from the boundary layer. So the question becomes, is this boundary layer correction negligible as compared to the delta T that arises from the role model that I've shown you previously, or is this boundary layer correction much greater than delta TL, in which case it's governing the relationship between Nusselt and Rayleigh? Okay, so the main idea is that you have to balance the heat that is input inside that boundary layer, which is the heat source times the height of the boundary layer. You have to balance that with the diffusive flux of heat away from that boundary layer, which is lambda delta T divided by delta. This gives you an estimate for the temperature drop associated with the boundary layer. So the total temperature drop is the temperature drop of the role model that I've shown you previously. It's this guy, plus the temperature drop associated with the boundary layer, which is this second term. We have not quite evaluated this second term because we need to know what is the scaling behavior for the temperature boundary layer in that system. Okay, so let's consider first low Prandtl number fluids. In the low Prandtl number fluids, the thickness of the temperature boundary layer is also the thickness of the velocity boundary layer, because away from the velocity boundary layer, you have turbulent motion that is going to mix the temperature field effectively. This boundary layer is H divided by the square root of the Reynolds number. And the Reynolds number, you can still estimate using that free fall velocity that we have. So if you substitute this equation of delta nu in here, you get an estimate for the temperature drop associated with the boundary layer. Okay, so once again, this is the temperature drop associated with the role model. It scales as Prandtl to the minus 1/2, and the correction scales as Prandtl to the plus 1/2, which is negligible as compared to Prandtl to the minus 1/2 in the low Prandtl number limit. We conclude that in the low Prandtl number limit, we can forget about the correction associated with the boundary layer. The role model that I've shown you indeed governs the relation between the flux and delta T in that system, and so we get the standard mixing length regime, Nusselt scales as L over H square root of Rayleigh Prandtl. Now the situation is more complicated for large Prandtl number, which includes the Prandtl number of water in the experiment, which is of the order of 7. Because for a high Prandtl number fluid, the temperature boundary layer will be much less than the size of the velocity boundary layer. So the temperature field in the bandular, it will see a flow which looks like a uniform shear flow over the bandular of the temperature field. And if you look at the temperature equation in this uniform shear flow, you get a different scaling for the bandular of the temperature field. Okay, and it scales like the inverse shear to the power 1/3. You can replace using the value of the shear associated with the velocity bandular, and you get a scaling for the bandular thickness in terms of Prandtl and Rayleigh. If you insert that into the total delta T, you still have the value associated with the bulk roll model, and then you have the bandular correction, which scales as Prandtl to the -1/6, Rayleigh to the -1/2. So you can see that regardless of the value of Rayleigh, this correction will dominate in that case because we're considering high Prandtl number flows now. So for high Prandtl number fluids, the delta T will be governed by the bandular, but in a way that's different from a standard Rayleigh-Benard experiment. And that will lead to the Nusselt number that scales as L/h, square root of Rayleigh number, but the exponent in Prandtl will be 1/6. Okay, so that's the prediction associated with the bandular correction. And that's something we wanted to confirm. So Benjamin Miquel, who's a postdoc working with me, used his own code to try to validate that, or to validate that numerically. And so what I'm going to show you is the Nusselt number divided by square root of Rayleigh times Prandtl, so divided by the mixing length prediction. L/h is fixed in that study to 0.1. So for low Prandtl number, we've predicted that the mixing length scaling regime should hold, and so we should get a constant here. For high Prandtl number, we've predicted that Nusselt instead scales as a Prandtl number to the power 1/6, so we should have a Prandtl number to the -1/3 here. Okay, so Benjamin has done numerical simulations with his own code. You can see very many values of the Rayleigh number, and you should look at the colored symbols here. And here you have the Prandtl number on the x-axis. You can see that indeed this quantity is pretty close to being a constant here for low Prandtl number. Now this is a lim log plot here. There is a colored symbol here, but it's behind some white symbols. So over approximately 1 decade, I think this is pretty close to a plateau for Rescaled data. And then it goes from a plateau to an exponent that is very close to 1/3 at large Prandtl number. And you can see that large Prandtl number, in fact, is not so large. You know, even Prandtl number 310 to the -2, which is what you would have for a liquid metal, let's say, is just right at the transition between low Prandtl number and large Prandtl number. And, you know, at 0.1, you're already in the large Prandtl number regime. So, you know, that validates the theory. And to further validate that, we decided, well, what we could do, you know, is switch from no-sleep boundary conditions to stress-free boundary conditions at the bottom. If we switch from no-sleep to stress-free, then we're removing these velocity bandulars. And so we shouldn't see this new regime that goes like Prandtl to the 1/6. We should have the mixing length regime regardless of the Prandtl number. Okay, and indeed, the stress-free data are the empty symbols here. You can see, of course, there is a bit of a curvature here, but once again, it's a lim log plot. And this is quite compatible with the plateau. I think there are also some white symbols here, maybe behind the colored symbols, but we have between 2 and 3 decades here where it's a plateau. Okay, so that confirms the behavior. And finally, we've understood the scaling behavior in all 3 parameters of the problem. For low Prandtl number or stress-free boundary conditions, the Nusselt number is L/h times square root of Rayleigh Prandtl. That's the standard missing length regime. For high Prandtl number and no-sleep boundary conditions, it's the same thing except that the exponent in Prandtl number is switched to 1/6. For stress-free boundary conditions, it would be, again, the mixing length regime. Okay, so that's the end of this seminar. The main take-home message, I guess, if you had to remember one thing, is that you can bypass the bandulars of a Rayleigh-Benard experiment using some radiative heating combined with some effective cooling associated with the secular heating of the fluid, and that can lead to the mixing length scaling regime where the Nusselt number increases as the square root of the Rayleigh number. All right, I thank you for your attention. And I should thank all the people working with me, 2 grad students, Benjamin Miquel, who's a postdoc, Sébastien Maître, who's a researcher working with me. And I'd be happy to take any questions.